categorizes common functional groups into strongly activating, moderately activating, weakly deactivating, moderately deactivating, and strongly deactivating. Activating groups are generally ortho para directors. This is because electron donating substituents stabilize the uranium ion intermediate. There are two ways this happens, through resonance and through inductive effects. A common marker is a negative formal charge. Deactivating groups are generally meta-directors. This is because they withdraw electron density. A marker is a formal positive charge which lessens the stability of the ring and in turn deactivates the addition. There is an exception, however, to this rule. When a halogen substituent is present, they are deactivators because they are inductively electron withdrawing. However, they stabilize the uranium ion only when attacked at the ortho para location because of lone pairs. It is uncommon to have an ortho para director that is deactivating.
This chapter we went more into depth about what ortho, meta, and para are, which as we now know, ortho is a 1,2 disubstituted benzene, meta is 1,3, and para is 1,4. NO2 is a meta director. This is because it leads to the most stable resonance structures when reacting with a meta fashion. For example, when we react NO2 with nitrobenzene in ortho fashion, you get this as one of your resonance structures, and it has a positive charge on the carbon that's directly beside the nitrogen with the positive charge. So this is going to lead to a lot of destabilization within the structure. However, if you have a nitrobenzene react with NO2 in a meta fashion, you'll have these three different resonance structures, but none of them have that positive charge on the C that's directly next to the nitrogen with the positive charge, which is why NO2 is a meta-director, because these are all a lot more stable.
When carrying out an electrophilic aromatic substitution on a disubstituted benzene ring, you have to consider both substituents attached to the ring. So in this first example, we have a CH3 group and an NO2 group. So you have to consider where both of these substituents are directing the new substituent to add. So the CH3 group is asking it to add in the ortho position, and the NO2 group is asking it to add in the meta position. But in this example, it's both substituents are asking it to add to the same location on the ring, so when the reaction's carried out, it gets added with no problems and you have a high yield. But in the second example over here, both of the substituents, here we have a CH3 group again, and it's asking it to add to the ortho or the para position, but then when you have the NO2 group asking it to add to the meta position, there are different locations along the ring. So in that case, you have to look at which substituent on the ring, the CH3 or the NO2, you have to see which substituent is the stronger activating group. So in this case, it's the CH3 group, it's the stronger activating group. So when the reaction's carried out, the CH3 group directs the NO2 substituent to add to either the para position or the ortho position.